Good morning, distinguished colleagues and esteemed guests. It is an honor to be here today. We are pleased to present our research on mathematical interpretation of tumor heterogeneity, analysis of the Fisher-KPP equation, and RD-ARD model. So this is our brief outline. Glioblastoma, or GBM, is one of the most aggressive types of brain tumors. Even after treatment, it tends to recur and progresses very rapidly. But what makes GBM particularly dangerous isn't just its growth, it's the fact that it shows a high level of intratumoral heterogeneity. As cancer cells keep mutating, they develop different characteristics. Some cells grow and divide quickly, while others are better at invading surrounding tissues. This diversity makes GBM harder to treat and predict. Because of this complexity, simple tumor growth models aren't enough to explain how GBM actually spreads. We realized that we need more sophisticated models that can capture this heterogeneity.
Even though cancer treatment technology has advanced, it's still very difficult to fully predict or control how a tumor will grow and invade. Especially when planning treatment strategies, quantitative analysis of tumor spread is crucial. But since tumors don't just grow uniformly, they grow through complex interactions of various cell types, simple models for short. That's why, in this study, we focused on analyzing how these different types of cells within the tumor interact and spread. We wanted to understand why a more precise mathematical model is essential for describing this behavior. To really understand the nature of GBM and find more effective treatment strategies, we need models that reflect heterogeneity. This approach has the potential to be applied meaningfully in cancer research and hopefully in clinical practice as well.
Now, let's break down the meaning of each term in the Fisher-KPP equation. The term d in front of the second derivative represents the diffusion coefficient. It describes how fast the tumor cells spread spatially over time. The second part, Ru times 1 minus u, models the growth of tumor cells using a logistic function. It means that the cells proliferate rapidly at first, but as the population becomes dense, growth slows down due to crowding effects. Let's define the variables. D means diffusion constant, which is the rate at which cells disperse. R means growth rate of the cell population, and K represents carrying capacity, which is the maximum possible cell density. U as the function of x and t means tumor cell density at position x and time t. Ru represents rapid cell growth. 1 minus u is a regulatory term that limits growth as the population nears its maximum. In this model, u equals 0 means there are no tumor cells, and u equals 1 means the cell density has reached its maximum. As time passes and depending on the location, u as the function of x and t changes, representing tumor growth and invasion. The value of r controls how fast the tumor grows. A larger r means faster growth, while a smaller r leads to slower growth. Non-dimensionalization refers to the process of redefining variables by incorporating physical quantities to eliminate some or all physical dimensions from an equation. This process allows the Fisher-KPP equation to maintain the same form across different tumor types, despite variations in the diffusion coefficient, reaction rate, and carrying capacity. First step is to set the non-dimensional variables. The spatial variable is scaled by a characteristic length to define a dimensionless spatial variable. The characteristic length is determined using the diffusion coefficient and the reaction rate. This transformation ensures that spatial measurements are represented in a dimensionless form based on the natural length scale of the system. The time variable is scaled by a characteristic time to define a dimensionless time variable. Here, the characteristic time is chosen as the reciprocal of the reaction rate. This scaling normalizes the time dynamics according to the inherent reaction time scale of the system. The dependent variable is scaled by the carrying capacity to define a dimensionless variable. This normalization confines the value range of the dependent variable between 0 and 1. Through these transformations, the Fisher-KPP equation can be expressed in a dimensionless form, allowing for a unified analysis across different systems with varying physical parameters. This approach simplifies the mathematical treatment and enables the comparison of tumor growth dynamics under different biological conditions.
From now on, we will talk about transformation of partial differential operators. The time derivative is transformed by expressing it in terms of the dimensionless time variable. This involves applying the chain rule to convert the original time derivative to its dimensionless form. The spatial derivative is similarly transformed by rewriting it in terms of the dimensionless spatial variable. This transformation adjusts the spatial differentiation according to the characteristics length scale. To comprehend the nature of the Fisher-KPP equation, it is crucial to observe that the right side of the equation has two steady-state solutions. These solutions correspond to the states where the system remains unchanged over time. The solutions are valid across all spatial and temporal domains. From a biological perspective, represents the absence of a tumor, while indicates the maximum tumor density. Analyzing how the solution graph evolves between these two states allows for a quantitative understanding of nonlinear tumor propagation. The Fisher-KPP equation describes the dynamics of traveling waves, where the wavefront connects the unstable equilibrium to the stable equilibrium. This transition region exhibits a wave-like behavior that propagates through space over time. The speed and shape of this traveling wave are essential for modeling various biological processes, including tumor growth and invasive species propagation.
The concept of nonlinear traveling waves can be more precisely analyzed using phase-plane analysis. By seeking a solution in a moving coordinate system, the Fisher-KPP equation can be transformed into a system of ordinary differential equations. To achieve this, a new spatial variable is introduced, which depends on both time and space. This transformation involves defining a moving frame of reference with a constant wave speed representing the propagation velocity of the traveling wave. Since the function describing the tumor density evolves as a traveling wave, the original density variable can be rewritten in terms of new dependent variable within the moving frame. By differentiating this new spatial variable with respect to time and space, and substituting these derivatives into the Fisher-KPP equation, it is possible to derive a system of ordinary differential equations. Using these variables, the Fisher-KPP equation is transformed into a system that characterizes the spatial and temporal behavior of the traveling wave. When represented on a phase plane, this system allows for the analysis of how tumor density evolves over space and time, providing a comprehensive framework for understanding the propagation of nonlinear traveling waves.
Phase-plane analysis is a method used to visually interpret the behavior of solutions to a system of two coupled ordinary differential equations by representing their trajectories in a two-dimensional plane. This technique illustrates how the solutions of the differential equations evolve over time using directional arrows to indicate the flow in the phase space. In this context, the UV plane serves as the phase plane for analyzing the system. Here, U and V are used as the axis, representing the tumor cell density and its rate of change, respectively. The trajectories in this plane depict how the system evolves as time progresses. A key concept in phase plane analysis is the identification of fixed points or critical points where the system's dynamics remain stationary. To locate these fixed points, the conditions for the time derivatives of U and V being 0 are applied to the system of ODEs. From these conditions, it can be shown that the system has two fixed points the point 00, and the point 10. The first fixed point corresponds to the point 00, representing the absence of tumor cells. By analyzing the Jacobian matrix at this point, the stability of this state can be assessed, providing insight into whether tumor growth initiates when the initial tumor density is very small. On the other hand, the second fixed point corresponds to the point 10, indicating that the tumor cell density has reached its saturation level. Due to the nonlinear term in the Fisher-KPP equation, the tumor growth rate approaches 0 as u nears 1. By evaluating the Jacobian matrix at this point, further insights into the tumor propagation speed and the shape of the traveling wave front can be derived, providing a comprehensive understanding of the system's dynamics.
In order to analyze the system of differential equations on the phase plane, we first rewrite the system in matrix form. To do this, we use what's called the Jacobian matrix. The Jacobian matrix is useful because it summarizes how each variable in the system changes with respect to small changes in the other variables. It essentially captures the local behavior near equilibrium points. For our system, the Jacobian matrix is constructed by taking the partial derivatives of each equation with respect to each variable. Specifically, we calculate the partial derivatives of the first equation with respect to both x and y to fill in the first row, and the partial derivatives of the second equation with respect to x and y to fill in the second row. This results in a matrix that looks like this slide. Once the partial derivatives are calculated, the Jacobian matrix is fully defined. This matrix will be key for understanding how the system behaves near critical points when we proceed to calculate the determinant and eigenvalues later. Once the partial derivatives are computed, we can fully define the Jacobian matrix. This gives us a clear picture of the system's local behavior near equilibrium points. Next, to further analyze the system, we derive the characteristics equation. We do this by subtracting lambda times the identity matrix from the Jacobian matrix and calculating the determinant. This leads to a quadratic equation in lambda where the solutions, the eigenvalues, determine the system's stability.
The key point here is the discriminant d of this quadratic equation. Depending on whether d is positive, 0, or negative, the nature of the eigenvalues changes. So by examining the eigenvalues and discriminant, we can classify the system's behavior and visualize how trajectories evolve on the phase plane. After understanding the theory, we can visualize the system behavior using Python. Using libraries like NumPy and Matplotlib, we plot the trajectories of the system in the phase plane for different discriminant values. In the 2D plot, when d is positive, the trajectories approach the equilibrium point in a straight, monotonic manner. When d is 0, the system slows down as it approaches the critical point. And when d is negative, the trajectories spiral into the equilibrium, reflecting the complex eigenvalues. We can also extend this to a 3D plot by adding a time component or an additional variable, giving us a clearer view of how the system evolves dynamically over time. Through this Python implementation, we can visually confirm how the mathematical classification translates into actual system behavior.
To mathematically describe GBM behavior, one commonly used model is the Fisher-KPP equation, a type of reaction diffusion partial differential equation which we've just seen. This equation can simulate both the in vitro and in vivo spread of GBM tumors. Clinical studies have shown that patients with less invasive GBM tumors, as described by the Fisher-KPP model, often have better surgical outcomes. However, the Fisher-KPP equation assumes homogeneous tumor cell behavior, which is likely not valid for highly heterogeneous GBM tumors. For example, MCTS models reveal that the central region of a GBM tumor expands more slowly compared to the invasive front, something the Fisher-KPP model cannot capture. Additionally, from both biological and mathematical perspectives, the go or grow hypothesis has gained attention. This hypothesis suggests that tumor cells either migrate or proliferate, but not both at the same time. To represent this behavior, more complex mathematical models beyond Fisher-KPP are required.
The RD-ARD model is designed to mathematically describe the heterogeneity and complexity of GBM, which cannot be fully explained by simple tumor growth models. In this model, we consider two distinct cell populations within the tumor. The first population, denoted as U1, follows a reaction diffusion equation. These cells primarily represent the ones with high proliferation ability. On the other hand, the second population, U2, follows an advection reaction diffusion equation. These are the model cells, meaning they tend to migrate and invade surrounding tissues. An important feature here is that U2 includes an advection term which models this increased mobility. This structure allows us to capture not only the growth of the tumor, but also the spatial interactions between different cell types. One key strength of the RD-ARD model is that it reflects the go and grow hypothesis, which suggests that tumor cells either focus on proliferation or on migration, but not both simultaneously. In summary, the RD-ARD model helps us better understand the spatial heterogeneity and invasive behavior of GBM tumors, which are critical challenges in developing effective treatment strategies. One of the key features of the RD-ARD model is that it better reflects experimental observations. Specifically, it captures how the invasive front of the tumor moves faster and more aggressively compared to the proliferative core. This characteristics aligns with the go or grow hypothesis, which suggests that tumor cells tend to either proliferate or migrate, but not both simultaneously.
Now, let's look at the actual simulation results using data from the glioblastoma cell line. On the left, you can see the simulation outputs for each model. Notice how the RD-ARD model captures the invasive front, particularly around the 0.1 cell density region. In contrast, the RD and ARD models fail to capture this feature accurately. To further evaluate model performance, we calculated the SSE, sum of squared errors, and AIC, archive information criterion, values for all four models. These metrics summarize how well each model fits the experimental data. Lower SSE values indicate fewer errors between the model predictions and the actual data. The AIC value helps us assess more quality balancing fit with model complexity. A lower AIC score means better model fit with minimal information loss. As shown on the right, the RD-ARD model consistently shows the lowest SSE and AIC values despite having more parameters than other models. This demonstrates that the RD-ARD model is not only more complex, but also more accurate and reliable in describing the behavior of glioblastoma cells. On this slide, I will briefly compare the four models used in this study. First, the RD model or reaction diffusion model assumes a single population of tumor cells that undergo diffusion and proliferation. It's the simplest model. Next, the ARD model adds an advection term to describe cell movement influenced by external forces in addition to diffusion and proliferation. The RD-ARD model describes two populations of cells, both following reaction diffusion behavior, meaning both diffuse and proliferate but without advection. Finally, the RD-ARD model considers two distinct cell populations. One follows reaction diffusion dynamics, while the other follows advection reaction diffusion dynamics. This model is particularly important because it reflects how part of the tumor cells are highly motile and influenced by advection, while the overall cell population also experiences diffusion and proliferation. One key feature of the RD-ARD model is that it captures the faster-moving invasive front of the tumor, aligning with biological observations and the go-or-grow hypothesis. It provides a more realistic description of the spatial heterogeneity within the tumor.
Now, let's move on to the performance evaluation of the four models. We compared the models using two key metrics, SSE, which stands for Sum of Squared Errors, and AIC, the Akaike Information Criterion. The SSE measures how closely the model's predictions match the experimental data. A lower SSE means the model has smaller errors and better fits the data. The AIC takes into account both the model's fit and its complexity. A lower AIC score indicates a better balance between accuracy and simplicity, minimizing information loss. This result demonstrates that the RD-ARD model achieves the best fit and performs better overall, proving its effectiveness in describing tumor behavior. Finally, let's look at the simulation results using data from the certain glioblastoma cell line. Here, the graph shows the simulation outputs for each model. What's notable is that the RD-ARD model accurately captures the invasive front of the tumor, particularly around the 0.1 density region. In contrast, the RD and ARD models fail to represent this invasive behavior clearly, while the RD-ARD model also lacks this precision. This shows how the RD-ARD model not only fits the data well statistically, but also realistically reflects the biological process of tumor invasion and spatial heterogeneity. In conclusion, the RD-ARD model stands out as the most suitable model for analyzing and understanding the growth and spread of heterogeneous tumors like GBM.
In this part, I'll explain how we used RD-ARD model to classify glioblastoma cell lines based on the go-or-grow hypothesis. To better understand the differences and similarities between various cell lines, we performed hierarchical clustering using the model parameters from the RD-ARD model. As a result, the cell lines were grouped into four clusters: high activation, go, low activation, and go or grow. The first cluster, characterized by the first cell population showing high diffusion and proliferation rates, while the second population shows lower diffusion and growth but higher advection rates. In the second cluster's cell line is distinct in that both cell populations have high diffusion but low growth rates, meaning they mainly focus on migration rather than proliferation. The third clusters, most of the cell lines here show low diffusion, growth, and advection rates, indicating a low activity state. Lastly, the fourth cluster, labeled as go or grow, includes cell lines where the first population has low growth but high diffusion and advection, reflecting significant heterogeneity and invasive potential. Additionally, when we applied parameter-based classification, we found that 6 out of 18 cell lines were classified into the go or grow cluster. These results closely matched the hierarchical clustering outcome, confirming the reliability of the approach. In summary, the RD-ARD model effectively distinguishes the diverse behaviors of glioblastoma cells, highlighting the role of heterogeneity and supporting the go or grow hypothesis.
In this study, we explored how mathematical models can play a crucial role in understanding the growth and spread of tumors. Specifically, we focused on comparing the Fisher-KPP equation and the RD-ARD model, analyzing how each model explains tumor invasion and identifying their limitations. The Fisher-KPP equation is a classic reaction diffusion model. It describes tumor cell proliferation and diffusion by incorporating key factors like growth rate, diffusion constant, and carrying capacity. Using this model, we simulated the spread patterns of solid tumors, such as GBM, and analyzed how changes in parameters affect tumor growth speed. We also worked on non-dimensionalization in a standardized way.
However, one clear limitation became apparent. The Fisher-KPP equation assumes that the tumor spreads homogeneously, which doesn't accurately reflect the highly heterogeneous nature of GBM tumors. For example, experimental models show that the central region of a GBM tumor grows more slowly than invasive front, something Fisher-KPP fails to capture. So to create a more realistic model, we turned to the RD-ARD model. This model is an extension that considers two distinct populations of tumor cells, one group with high proliferation rate and another with higher motility. Through this analysis, we were able to mathematically model how these two types of cells are distributed spatially within the tumor and compare it to simple models. The RD-ARD model turned out to be much more effective at reflecting the differences between the invasive front and the tumor core and provided a more realistic description of tumors with high heterogeneity. We also used the difference in wave speeds, denoted as delta C, to quantitatively analyze tumor heterogeneity. This allowed us to interpret the relationship between cell density and diffusion behavior in a more precise mathematical way.
Additionally, we conducted clustering experiments on GBM cell lines based on their proliferation and motility characteristics. The results clearly showed distinct groups, confirming the go-or-grow behavior, where cells either migrate or proliferate but not both at once. This further supported the RD-ARD model's ability to describe tumor heterogeneity in detail. Overall, this project wasn't just about looking at cancer as a biological phenomenon. It was about exploring how mathematical approaches can deepen our understanding of tumor behavior. The analysis using the RD-ARD model helps explain spatial heterogeneity in GBM effectively and can potentially be applied in developing personalized treatment strategies. Moreover, by analyzing the model's parameters, we can gain insight into each patient's tumor characteristics and better understand the signaling pathways that regulate tumor's growth and invasion. Looking ahead, we believe this approach can be expanded to reflect tumor spread in even more complex environments or combined with real clinical data to create mathematical models with real predictive power. We deeply appreciate this opportunity to share our findings with you today. Thank you all for your time and attention.